Well, so it's 9 o'clock, so why don't we get started? 9 o'clock in California, that is. So I'd like to thank you all for joining us today for um, the IEEE SUSTEC webinar series on technologies for a circular economy. Let's remember that we need to be thinking about circular economies because in this world of finite resources and mounting environmental challenges, the traditional linear model of take, make, and dispose is no longer viable. Um, we really need to be thinking in terms of what I'll call a womb to tomb circular economy. And then I want to remind everybody of the role of the IEEE, which is to ensure that our response to climate change is substantial, appropriate, and properly engages IEEE, its members, and the larger technical professions. This is what Saifur Rahman said a number of years ago. IEEE provides a neutral platform and is a technology provider. This is a set of talks brought to us by Future Directions and the IEEE SUSTEC initiative, um, and in part with the IEEE SUSTEC conference. It's intended for a broad audience, for the general community, and it's serving the needs of the profession and the public by increasing awareness and understanding of technologies. Here we are today with a introduction to regenerative design by Alan Booker. Um, Next talk will be part two in this series where he will give case studies in regenerative design. And then an upcoming one in September 11th will be Ravinder Dahiya talking about circular electronics. And today's talk will show how nature's solutions to creating a circular economy have a lot to teach us about building regenerative and sustainable technology. Um, so with that, I'll give a very brief introduction to our speaker by saying that I was at a conference recently and they had a ribbon that I thought was really good for me. It said, "I used to be somebody." Well, if we were at a conference and Alan got a ribbon, he'd get one that should say troublemaker. So with that, Alan, if you want to pull up your slides and take it away.
All right, I'll let you stop sharing your slides and then I can bring mine up. There we go. Hopefully that's got it going.
Looks good.
Excellent. Yes. So I think maybe the abstract you had there was one for another talk that I gave at the Circular Economy workshop at the SUSTEC conference. What we're looking at today is an introduction to regenerative design, and I'm going to do a remix of a few things that I've presented before because they all come together to really cover this topic. And um, I guess what I would start off with is just a little background for me is I got out of a undergrad in electrical engineering back, well, a long time ago, and got into the new world of the internet as it was just coming really online and becoming publicly accessible, and got involved with really helping to scale that up and a lot of the technologies that made the internet possible at a global scale. And as I was doing that, I started to look at and understand the degree of damage that was being done by a lot of the engineering practices that we were doing and started asking the questions. And this was in the early 1990s, so there wasn't a lot of discussion. Even back then, there weren't advanced degrees that were out there in sustainable design, much less thinking about regenerative design. And so I was one of the early instigators and troublemakers asking a lot of these questions. And talking about sustainable design and then looking at it as we got deeper into the analysis, understanding that a lot of the ways that sustainable design were and sustainability were being defined were actually not possible. And I'm going to get into that just a little bit today and why we look at regenerative design and how I've come to redefine sustainability. And so you get a little bit of a preview of some of a book that I'm working on at the moment that we hope to release a little later this year. And so that's how we're going to kind of get into. And I'm going to start with um, something that I shared several years ago at the IEEE Town Hall for the Planet Positive Initiative. But I think it's good initial framing. And so I'd like to come back to it. And this is something that I got the idea from another presenter many, many years ago and sort of developed into a critique of our modern engineering approaches and how we think about things and how we have become what I think of as overly impressed by our own engineering abilities. And so what I'd like to do is I would like to do a comparison of high tech and low tech. And so the picture I have here, this is actually in North Carolina. This is standing up on the deck in a building and looking out over an array of solar panels in a garden and polycultured orchard. And you can see the beehives there in the middle distance and more solar panels off even further in the distance and so forth. And so this is me saying, let's compare and contrast the engineering of the high tech and the low tech here. And so let's start by looking at the attributes of the high tech. And I'm going to list them off. Let's go to it. How about this? That it harvests energy from sunlight to support immediate needs while storing excess energy in a stable chemical form for future use. It manufactures complex chemical compounds that serve as feed for humans and animals. It also creates thousands of medicinal compounds along with various other functional and structural materials. It cleans the air and emits available diatomic oxygen while breaking down CO2 and sequestering the carbon in the soil in a stable form. It stabilizes the soil surface, it prevents soil erosion, it builds soil fertility. It shades the soil, it moderates the soil temperature and allows efficient rain absorption. And it moderates the impact of the rain, preventing soil surface damage. And by the way, if you haven't figured it out by now, yeah, the garden is the high tech, right? It destroys the soil structure and the tilth. It decompacts the soil, it builds organic matter content in the soil and increases its water holding capacity, thereby improving the groundwater hydrology. It pulls water from the subsoil, humidifies the soil surface, and pumps moisture into the atmosphere via evapotranspiration, helping restore the atmospheric hydrologic cycle. And it incubates bacteria such as Pseudomonas syringae, which you've got an electron microscope image of here on the left, that seeds the atmosphere and becomes condensation nuclei, further helping regulate the large and small hydrological cycles by creating a biotic pump. And by the way, what's interesting is that comment about the bacteria seeding back when it was originally made in the late 1980s was quite controversial. Today, there are a good number of scientific papers that have shown that very rigorously. And what's interesting now is they're showing that these bacteria are actually much superior condensation nuclei to dust particles because of their structure. And they tend to result in more moderate and more reliable rains. So, yeah, they're quite important for the maintenance of moderate climate events. And, you know, this whole system builds itself by harvesting all the energy materials it needs directly available in the local environment. There aren't supply trucks, there's not 18-wheelers arriving with materials trucked in from overseas in order to build all of this, right? It is able to harvest all of its energy and all of its materials ambiently from the local environment. It automatically forms a complex network of relationships between the elements that allow for adaptive and resilient system performance. It self-repairs and self-replicates, automatically creating new generations better adapted to the prevailing environmental conditions. It repays the embodied energy of production within the first few days of active operation and is then net energy production positive for the rest of its operational cycle. The system does all this while providing great aesthetic value with zero toxic chemicals and no waste products. All components of the system are automatically recycled with near 100% efficiency as a byproduct of system operation. All right. So that was the high tech. What about the low tech? And of course, yep, we're talking about the solar panels and the associated hardware that goes along with it, right? Well, it harvests and stores energy from sunlight only, really has no other major functions, right? It takes 4 to 5 years to return the energy invested in construction. Now, some people will go, wait a minute, the solar panel, I'm not talking about the solar panels. The solar panels, the batteries, the charge controllers, the inverters, all of the pieces, parts that have to go into it. And that's probably conservative. It probably takes longer than 4 to 5 years, but we'll just say that the entire, because we have all the copper wiring, all of the other infrastructure that's required to make it functional to deliver power to, say, a load and to buildings, right? Um, yep, it produces toxic byproducts in both its manufacturing and its recycling. And it has a limited service lifetime and will not repair or replicate itself. So, what I'm suggesting here is that the technologies that we have right now, by and large, are incredibly primitive and very inelegant. We have a long way to go to creating technologies that can even begin to compare to the output of the 4 billion year R&D cycle that life on Earth has gone through in order to be able to create robust, resilient, and regenerative systems at scale that have been able to adapt to and function in the face of um, large disturbances over time and come back and be able to recover and continue functioning. So I'm going to suggest that we have a lot to learn about regenerative and resilient design from how life does it, and to learn how to what we do in what we call in regenerative design science stacking functions, which is looking at how life has managed to create structures and technologies that serve multiple functions simultaneously by being a part of a reciprocal network of beneficial interrelationships, of thinking in terms of flows and patterns of beneficial interrelationships instead of simply being focused on the dynamics of single elements. And actually embracing complexity instead of attempting to linearize and destroy complexity in a system. Because one of the things that I have looked at, and we'll talk about a little bit from the thermodynamics of it, is that regenerative system dynamic is an emergent property of complexity. And when we try to nail things down and make them linear and simplify them, we also tend to make their dynamics purely mechanistic. And all mechanistic system dynamics we've identified so far are degenerative, and as they actually succumb to entropy instead of regenerative, which means that they manage to actually go uphill against the entropic gradient. So with that, let's go into redefining what we mean by the words regenerative and sustainable. And this is going to be a little bit of a preview of some of the thinking that I'm laying out in a book coming out called The Dynamics of Regenerative and Sustainable Holons. And for those of you who aren't familiar with the word holon, a holon is a coherent whole. And I won't get into defining it too deeply today, except to say that If you get into general systems theory and you look at how Bertalanffy et al. Have defined systems, um, you start to see that it started out from a more mechanistic approach to systems in which the elements that make up a system are assumed to be a bit more static. Whereas in a holon, we understand that a coherent whole is not defined by its elements so much as it is defined by its pattern of interrelationships and flows. And the concrete example of that's simple. A bicycle versus a forest, right? A bicycle is a system, and presumably you don't want parts of the bicycle entering and leaving the system while you're trying to ride it. That would generally be considered an undesirable behavior. On the other hand, the forest is not defined exactly by its collection of elements, the set of elements, that is by the trees and the birds and the animals and the water flowing through. Because what's happening? Well, in any given moment, birds are flying in and out of the forest, and water is flowing through, and air is moving through, and trees are being born and trees are dying. So if we went away from a forest and came back 1,000 years later, that forest might still be there, but not a single element that was originally in that forest living element might still be there. Maybe every living element has been replaced. But we would still say the forest is still there because the pattern of interrelationships and flows that create the ecology of the forest are still in place. And so when we talk about holons, we're thinking more in that definition, systems definition of understanding systems dynamics through the interrelationships and patterns of flows than we are in terms of defining primarily in terms of a set of elements that are secondarily characterized by their interrelationships. So let's go here first, right? The very famous Brundtland Commission definition of sustainability that has been picked up and used quite a few places. And it says, of course, sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. And my critique of this is that this is not actually a working engineering definition. It's a good vision statement, but you can't engineer from this broad conceptual statement. And what I mean by that is there's probably folks maybe on the call who've had to do things like design a step-down transformer or design parts of a power transmission system or design elements of a cloud computing platform or so on and so forth. And if I came up to you and said, all right, our definition of sustainable is that, and I want you to rigorously show whether you have met that definition or not. How do you get a handle on that? Is there anything metricable at the individual element level that you can work with that? Because that is, as we said, it's a broad vision statement. And what it's basically talking about is the emergent property of all of the technology in our technosphere working together. That is up at a level at which it is impossible to metric for a working designer, an architect, an urban planner, an engineer. You can't really get your hands around it because you can't say whether your individual piece is actually sustainable if that is your goal, your definition. So what I'm going to suggest is that we need to look at and come to a different way of understanding how we're going to define sustainable. So the question that pops up that goes back to our high tech versus low tech question is this. How is this? And what I mean by this, talk about this forest here, right? How is this possible without violating the second law of thermodynamics? Because, for those of us who had to go through engineering school or maybe physics or, and had to take thermodynamics, we typically concentrated on mechanical statistics side of thermodynamics that looks at systems in which entropy is always increasing monotonically, um, right? And the answer is no. If you looked at it carefully, you'd realize that when you looked at certain kinds of even mechanical systems, we would see decreases in entropy in one part, increases in entropy in another part. And the second law basically says that the increase over here will, and the sum of all the increases will always outweigh the sum of all the decreases. And therefore, in that whole closed system, the entropy is always going to increase. And what's, of course, interesting is that planet Earth is not a closed system, right? We can dump entropy into outer space, and we do. We have very high density incoming energy from the sun, and then we dump high entropy, low density energy as infrared radiation primarily into space. And what that creates is a thermodynamic gradient in which pockets of negative entropy are actually possible. And life basically surfs that thermodynamic gradient and creates large areas of negative entropy because the positive entropy that offsets it is being dumped into space. So that would not be possible if Earth were a thermodynamically closed system, but because Earth is a dissipative system that creates dissipative structures, it's possible, right? And so defining regenerative and sustainable systems requires that we answer that question in that way because it explains to us how we have to, if we're going to create technology that is regenerative, then that is the pattern that we have to be embracing. And we can then look at and ask ourselves, are we creating systems that, as a totality, create pockets of negative entropy and self-organization, and then export extra entropy into a place that actually works with that. So if we look at and want to define a regenerative system, then we would say that a regenerative system is one who has the capacity to build, organize, and repair itself, actively working against entropy to adapt and renew its function over time. And of course, as we've seen, our main model of regenerative systems are living organisms, which do surf that entropy gradient between concentrated energy coming solar energy and the diffuse radiation loss to space to create those regions of local negative entropy. And that allows them to grow in both complexity and function over time, requiring no external help to regenerate. Another hallmark, of course, of regenerative systems is they stay within ecosystem limits via feedback loops that allow them to stabilize at a point of dynamic equilibrium with the surrounding environment instead of growing monotonically until they reach a point where catabolic contraction is the only means of survival. And catabolic contraction, of course, means that catabolus literally means self-eating, which basically means scavenging parts of your own infrastructure in order to power your ongoing function, right? So catabolic contraction is the point in which a system has overshot its resource base and therefore must undergo catabolic metabolism in order to shed complexity and get back to a point where some sort of homeostasis can be met, right? So this implies that self-organizing and self-limiting behavior is built into the dynamics of regenerative systems. And that being regenerative is an emergent property of complex adaptive systems, living systems, and ecological systems in a high state of function. And by the way, the feedback loop picture here, as you probably have already deduced by glancing at it, is just a simplified version of the positive and negative feedback loops that drive parts of the homeostasis of the atmosphere, right? And you have to have both those positive driving feedback loops and then the controlling and limiting negative feedback loops happening in order to be able to drive a dynamic homeostasis that is driving, yeah, that maintains itself in some sort of stability over time, right? So reducing network complexity in an effort to create a more orderly or easily understood system will almost always result in a less regenerative outcome. Regenerative behavior is an emergent property, so attempting to linearize a system will inevitably prevent it from exhibiting a regenerative system dynamic. This is quite interesting because, of course, one of the things that if most of us who went through engineering school or other design, professional design training programs, the whole idea was to simplify, to linearize, so we get a handle on it, we can make it predictable, we can make it controllable. And what is interesting about that is that it basically is training us to be anti-life because life is inherently complex. It is inherently unruly. It's inherently unpredictable because complexity, as complexity science has shown us over the last couple of decades, has limits to how much we can predict about and control its behavior over time. Or as the saying goes, you cannot control a complex system. You can only present it with stimuli that will affect its behavior. And so as designers, we've been trained not to like having to work with complex systems. What that's basically done is it's taught us to take anything that's living and nail it down and make it dead so that it is easier for us to get our a handle on and control. So what I'm going to do first is I'm going to give you a very simplified version of my thermodynamic definition of regenerative. The full definition with equations and all will be in the book, but we could simplify it down and say from a thermodynamic perspective, thermodynamics, a system could be called to be regenerative if it harnesses ambient energy flows from its environment to power its own operation, thereby creating a local region of negative entropy that allows it to self-organize, generating internal patterns of structure, flow, and interrelationships that increase over time until they reach a state of dynamic equilibrium, the complexity of which is determined by the magnitude of the energy gradient available to the system. Obviously, the larger the energy gradient and the more information and material flow that's available to the system, the more it's possible to take those energy and information and material flows and create complex, highly functional systems. And very importantly, if it's truly regenerative, the system will reduce complexity and establish a new equilibrium point when the ambient flows are reduced. So instead of collapsing, it will be able to shed complexity and meet a new homeostasis point, right? So far, the only systems we have on the planet that can do that in and of themselves that I'm aware of are living organisms. So we have to ask ourselves the question, how do we get to regenerative technologies? And there are two basic ways in which a human design technology could possibly be designed to be regenerative, right? The first is that the technology could exhibit self-organizing properties such as those seen in living systems, thus allowing it to self-regenerate. And we're not really there yet with any of our technologies that I'm aware of that can truly do that. I mean, do what a tree can do, which is like, yeah, we give it a little, here's the seed. It has information stored inside of it in the form of DNA and genetic information, and it's epigenetic information that's also stored in there. And it has a small amount of energy in the form of starches that give it its getting started capability. And once it uses that initial energy burst that given to it by its parent to be able to put up its first leaves and begin to photosynthesize. And from there, it begins to self-power, to self-organize, to grab oxygen and carbon from the atmosphere, and to create and to its own self-metabolism. It literally can grow into a huge tree with a root system and leaves and everything else. But just stop and think about the engineering of that and how amazing it is. And if any of you are, all of us that are engineers, if that was our requirements document, what, and you say, yeah, that's the technology you need to create. It'd be like, oh, wow, okay, you know, can our technologies do that? Can our technologies become self-regenerative? Interesting question. And but even asking the question begins to have us think in new directions, new possibilities, right? The second possibility for human design technology to be regenerative would be that the technology itself could be embedded in a larger system that includes self-organizing components that maintain and regenerate the technological component as a part of the larger system dynamic. And one example of how nature already does this is that's quite famous. I didn't add the slide on it, but is a termite mound. The termites in Africa had a quandary, right? The atmosphere there, the climate. Well, how are they going to survive that climate when you can get very hot and very dry? Well, they could have, from a strategy standpoint, they could have tried to physiologically create internal organs that would allow them to survive that, to be able to, cool themselves and to maintain moisture and so forth. They decided to do something else. They decided that they would come together as a colony, and the superorganism of the colony would create a termite mound, which is an external physiological organ of climate regulation. And so what happens is you can argue, and it has been argued by a number of scientists, that we need to think of that termite mound a as a bit of termite technology that if the termites go away, of course, the mound itself will degenerate. The mound by itself will not regenerate. However, as a part of this larger system of the termite colony, the mound itself is continually being regenerated because it is an integral symbiotic part of a larger superorganism, and its ongoing regeneration is an integral part of the regenerative cycle of that larger living system. So we could look at and think about creating technologies that are not themselves self-regenerative, but that are instead part of a mutually symbiotic network of interrelationships with living systems, including humans, that allow for those technologies to be regenerated over time as a part of the dynamics of the larger system, right? And here's a bit I haven't shared before. I thought I'd throw in for this particular webinar. As you probably think, it's like, wow, if I'm an engineer, I'm trying to figure out whether my particular part is regenerative or degenerative, then I got to go and do thermodynamics and figure out whether I'm net positive, net negative entropy, and so forth. That sounds a little daunting. And so that's not actually my ultimate workable definition. What I realized as I was working with this is that self-regenerating systems actually create and articulate patterns that show that they're self-regenerating. Because what happens is if they're degenerating, those self-organizing patterns begin to decrease and fall apart. And if they're regenerating, then those self-organizing patterns increase and come to a point of maximum complexity that is, as we said before, driven by the amount of available energy, material, and information flowing past them. So if we looked at it from more of a patterning perspective, we can become a little more actionable from looking at and thinking about this from a design perspective. So yeah, we still want to think about it harnessing ambient energy flows from its environment to power and sustain its own operation. Sure, that's actually measurable. Thereby articulating and improving its own internal structures and functional efficiency. Again, that's something we can look at more directly, while also articulating and improving the nesting and distribution of relational patterns between itself and its surrounding elements. In other words, we're not looking strictly at the internal structure of systems we're designing. What we're doing is we're looking at how it either is symbiotic, mutually symbiotic with the surrounding environment, or is it parasitically symbiotic and thereby degrading its surrounding environment, right? And participating in and supporting temporal and behavioral patterns that contribute to the larger system function, helping them increase in quantity and quality over time. So, is the thing that we are designing actually supporting temporal and behavioral patterns in the larger ecosystem, helping those patterns to increase in quantity and quality over time? Until the system itself and the larger whole that contains it moves towards a dynamic equilibrium whose complexity is bounded by the total energy, information, and material flows supporting it. And of course, I didn't put that in here, but yes, we still want it to be able to shed complexity and create a new homeostasis when those flows reduce, right? So what we've ended up with is a more functional definition of regenerative that can be looked at on the individual system and element level. And what's interesting is because it works with the approach to regeneration that life has come up with, what we know is that if all of our technological systems did this, that the emergent property of all of them interacting would be to move towards regenerative system dynamic instead of degenerative system dynamic, right? So now that we have a basic idea of what we mean by the terms regenerative and degenerative, how does this inform the creation of a more technically precise definition of the term sustainable? So, in the absence of adequate technical definition of sustainability, many groups have settled on a de facto approach that is now showing up in a lot of the standards, meaning sustainable being defined as operating at a point that is just barely not degenerative. And of course, there's two problems with this. The first is, well, how do you measure that, right? Um, and the second is that I'm going to argue, after looking at this in some depth, that in a complex system like the living biosphere, that is not thermodynamically a acceptable definition of the word sustainable, right? So there's a lot of diagrams that have been shown like this. This one happens to come from Daniel Christian Wall, the diagram here on the right. And it says, well, you got degenerating systems, we got regenerating systems, and then over on the right, it says sustainable, neutral point of not doing any more damage. And my argument is, and when we go into this in our more deep, in-depth classes, we spend a lot of time unpacking this and get into the technical details of it. But my conclusion after a few decades of looking at this is that that definition is not workable. So the idea of sustainable being something at the neutral point between regeneration and degeneration is not possible because the point is metastable and will almost always fall towards degeneration. In order to create a more functional definition of sustainability, we need to make a subtle but profound shift from using this term to describe the nature of the system dynamics, which should be characterized in terms of either regenerative or degenerative, and move over to thinking about sustainability as describing whether or not the system can maintain that type of system dynamic over time. So a sustainable system is one who is exhibiting a regenerative system dynamic and can maintain that regenerative system dynamic over time. Because we get into the problem of metastability, right? A system might temporarily exist in a metastable state of pseudo-balance between the forces of regeneration and degeneration, but will eventually settle out into one of those two dominant dynamics. And as we've said, if you look at the way that thermodynamics drives this process, if you're at the metastable point between regeneration and degeneration, you are going to tend to fall off towards degeneration. So I think it's a losing proposition to try to define sustainability as a neutral point. It's not an engineering robust definition with any level of safety to it. And when we're talking about whether or not we regenerate or destroy our entire biosphere, I would argue that we need a pretty good safety margin, right? So I'm going to give you a bit of another sneak peek at one of the conclusions from my book, as we said, The Dynamics of Regenerative and Sustainable Holons, with a simplified definition of sustainable. And again, the book will get into a more rigorous definition, but here it is. Sustainability is defined as the ability of a system to maintain a regenerative system dynamic over time. And again, the full technical definition defines the time periods and what that looks like and why. To recover to a desirable regenerative system dynamic when challenged with stressors. And again, the formal full definition talks about how much of a stressor and what the recovery looks like. And then three, create environmental conditions conducive to both the perpetuation of its own regeneration, the regeneration of the system in which it is embedded, and the regeneration of systems with which it symbiotically exchanges energy, information, and matter. Or as Janine Banyas famously put it, Janine Banyas being one of the progenitors of biomimetic and bio-inspired design, she said, life creates conditions conducive to more life, which is basically a way of saying that regenerative systems should create systems conducive to more regenerative systems. And that's what this third definition, this third requirement or criteria basically says, right? So there's you a definition of sustainable that is much more manageable because when we finish up with a technical definition, then I can give it to technical practitioners and ask them to look at whether an individual system actually meets these requirements or not, right? So I'm going to stop my presentation there, and if you're interested in a direct conversation with me, please reach out, and I'll be interested to hear that. But I'm sure we maybe have generated a few questions. So what I'm going to do here in a moment is stop sharing my screen and see what questions and discussion we might have. All right.
Well, Alan, it looks like we've just lost Charlie
Oh,
because I don't
okay.
hear him. I don't hear him. It's Micah. So
Hey,
what I
Micah.
will do is entertain you with the questions from the Q&A until Charlie comes back on.
Okay. Yeah.
So one question was about references, whether you would be
Yes.
able to share some references with the attendees so that they could further explore the aspects that you presented.
Yeah, my intent is when we get the book out, obviously to reference the book, and obviously here I'm trying to develop this argument in basically half an hour. So um, one of the challenges I think somebody asked the question, why are we not getting into more real life examples? It's like just to get through this overarching scaffolding of an approach. I'm not able to spend a lot of time digging into real world examples. We're going to try to do that in the next presentation, hopefully, and show a few more real world examples and so forth. But time constraints being what they are, yeah, I just had to it took me the whole time just to sort of make the argument from a technical standpoint. And hopefully we'll get into some more real world examples next time.
Yeah, so maybe for the at the next session, if you have a few references that we can post in the chat for the
Hmm.
people, then we can do it then. Charlie, you want to take over?
Sure. One of the troubles with this tool is if you're a panelist or a host, you can't enter a question into the Q&A. And so I was taken out anyway. I had one quick comment for you. You said solar panels don't provide any other action other than generating power. I do have a Tesla roof, which is tiles, and it is a very pretty roof, so it provides an aesthetic component.
Yeah, and one of the other things we could note is if we are very careful, we can even do things like agrovoltaics, which I've worked with before, which is putting and we I also I've worked with green roof structures where we put solar panels on on a green roof, such a way that the two are mutually symbiotic. The green roof helps keep the solar panels cooler, while the solar panels actually provide some dappled shade for certain parts of the green roof and allow for the growing of certain things on the green roof that aren't possible otherwise. In agrovoltaics, we can put properly spaced photovoltaics into pasture and provide, again, some shade that allows for certain things to happen in the pasture system. We can graze animals such as sheep underneath it. So, the traditional thing of just sticking normal solar panels on the top of a roof um, is obviously, oh, when we start letting the solar panels partner with life, now some interesting things start to emerge, right? So we're now moving in an interesting direction. And so I think that's a good little bit of nuance to that whole conversation.
Um, and then a question I have is I usually think about the terms of sustainable in terms of the carbon cycle, um, and contrast fossil fuels as not being sustainable versus renewable energies as being sustainable. Um, and if you go back, 500 years, heating was done with wood, and it was a sustainable thing because the wood kept growing back. Um, but uh, your
You're hitting one
comments
of
about
you're hitting one of
regenerative.
my you're hitting one of my hot buttons. So keep on going. But yeah,
So the question I would have is if you talk about regenerative versus sustainable in the context of carbon neutrality, could you speak about that? Or
no,
is that
because carbon neutrality is a red herring. I'll tell you why. We need to be talking about carbon cycling. First of all, carbon is not an enemy. What we need to be looking at is carbon is the basis of life. Carbon neutrality, it's like, no, we need to be looking at whether the carbon cycle is balanced. That is the way to look at it, right? And because carbon neutrality is a terminology that has to do with the mechanistic view of a living system, whereas living systems look at carbon cycling. The mere fact that carbon is released at some point is a natural part of ecosystem function. The question is whether the release and the sequestration, dynamic sequestration, is in balance from a living. That's actually how you have a dynamic homeostasis of carbon in the atmosphere, right? What's happened is we have disrupted fundamentally the carbon cycle by reducing active biomass, reducing soil sequestration, and so on and so forth. It's not merely that we have been burning fossil fuels, which is, of course, a huge contributor, but there are so many other. And then I was like, I've had this. This is why I basically told you, yeah, you got to introduce me as a troublemaker, because here we go. I've been in conferences before where I literally pulled out my periodic table and held it up and said, I don't know about all of you, but my periodic table has an awful lot more than carbon. There's nitrogen cycles. There's phosphorus cycles. There are sulfur cycles. There's molybdenum. All of life has all of these cycles. What we have done is we have become monotonically obsessed with the carbon, mostly because there's money chasing it. Let's be honest, okay? Because of the way that this has been done, there's money chasing people's research around carbon. And therefore, people have gotten obsessed by it. If we were to fix the carbon cycle, but we're not to fix all of the disruptions to the nitrogen cycle and the phosphorus cycle and the potassium cycle and all the other living cycles of the biosphere that supports us, we would still be in a degenerative system dynamic. So this idea that we're going to solve all of it by simply becoming obsessed with carbon is scientifically ridiculous. And we should call it out as that, right? And so I'm just gonna, that's why I said, no, I'm not going to get just obsessed with carbon, except to say that yes, we have to rebalance the carbon cycle as part of the whole thing of regenerating hydrological cycles. And by the way, the hydrological cycle is responsible for maybe 80% of the short-term thermal dynamics of the atmosphere, right? So weather instability a is a function of climate change. Climate change may be driven in a large part by the disruption of the carbon cycle, but then the dynamic swings that are causing energy extremes in our climatic system right now are being driven by disruptions in the hydrological cycle, coupled with the extra energy in the climatic system driven by disruptions in the carbon cycle. So, sorry, I could go on for that. I'll stop there, but yeah.
Um, so the other thing is my being taken out as a panelist, Micah, means that I can't read any of the earlier questions. So if you could go back
Okay.
and look at some of the other questions.
All right. Sure. Somebody pointed out a beehive, I guess referring to the termite solution.
Yes.
Uh, and it's just beehive question mark. So
Yes.
how?
Beehives are this exact same thing, right? The bees do the same thing. They actually come together as a superorganism, and they create a structure, a beehive, that is part of their physiology. And what's interesting is that, and their behaviors are part of their, like if you look at the immune system of a bee colony, what the bees decided to do is instead of invest a huge amount physiologically into the immune system of individual bees, they actually invested a lot more into the behavior of the hive as a group and into the structures like building propolis around them, which has antimicrobial properties and so forth. So it's exactly the same thing. You could argue that a squirrel's nest is also a same kind, and that any of these kinds of things that animals do are technologies, right? So you have squirrel technologies and bee technologies and termite technologies, and yeah, leave it at that.
The grand innovators.
Yes, yeah.
Okay, so here is another question, and it's Carol's. Would you say that AI may be the first human technology poised to become regenerative?
That's a really complicated question because there are two levels to it, right? One is that it it's the first technologies that we've really created that exhibit certain forms of complexity, like what's called structural coupling. And when I get into the deeper parts of the course and we start to go through all of this, we look at all these dynamics that complex systems actually exhibit. Structural coupling basically means that its own internal structure changes to reflect what it has learned. It's
Hmm.
basically our brain structurally couples, right? If you're listening to this conversation, then your brain is changing its structure and incorporating new information. That's called structural coupling, and AI can do that. Of course, underneath at the moment, we are running it on top of a lot of technology that is extractive and requires huge amounts of power to run. That in many cases, the data centers are taking and creating thermal pollution in water by taking water in and heating it up and releasing it back into the atmosphere and so forth. So yeah, it's quite interesting, right? Are we creating something that at one level is starting to exhibit behavior that is complex and that could start to give us some behaviors that we would classically think of as part of what begins to define a regenerative system, but the underlying structures upon which it depends are still degenerative.
Hmm.
Interesting, right? It would take a while to unpack that, wouldn't it?
Definitely a very interesting question.
So,
Um,
Micah, there is one question that's I can see and it's of interest to me. Um, there's a technique for optimizing circuits and designs called particle swarm optimization.
Mhm.
Is that an example of a regenerative design?
Well, that is a design process. What I am arguing is that you measure the whether a system is regenerative or degenerative on its dynamics. I would say that kind of approach is quite interesting because it allows for us to use approaches. This is basically a lot of these kinds of approaches come under the category of bio-inspired design or biomimicry. They're looking at how life has figured out to do things, and we start to pick up design ideas from that, right? Um, I'm going to say that my gut feeling is, after studying this for a while, that those bio-inspired design processes are more likely to move us in the direction of regenerative systems outcomes. But it's like, could you use that to design a system whose ultimate system dynamic was degenerative? I think so. So it's like, I think what we've got to do is we've got to ask, what is the actual function of the system when it operates? And then we can determine whether that is a regenerative system dynamic or a degenerative system dynamic.
Okay. Back to some of the other questions, Micah.
okay. All right. So Brian Sutherland was asking whether are biohybrid technologies like neural organoids designed to replace AI chips in computing potentially an example?
Yeah, this
And
becomes these are where things get quite interesting, and where we're starting to look at technologies that start to exhibit some of the self-organizing patterns of life. And it's both exciting and scary at the same moment, right? It's exciting in that it starts to hint at the possibility of self-regenerating human technologies. The scary part, of course, is I believe it was Bill Joy that originally pointed out what was he called the gray goo problem. Some of you may know it on AI as paperclip problem, which is any technology that can be potentially self-regenerating. If it gets out of hand, how do you stop it, right? So um, Bill Joy's argument when he first put it out, what in the gray goo problem was, what if you ended up with a self-regenerating technology that metabolized organic material and turned it into gray goo? And so it gets loose in the world and it begins to metabolize all living organisms and turn them into gray goo. And there's nothing to stop it. And so what ends up happening is this, nanite or, that sort of thing goes off and just kills everything, and turns it all into gray goo. So again, so self-replicating technologies and self-repairing technologies quite interesting, but they also, for us as engineers, we need to do a really thorough risk analysis to understand the possibilities of a self-replicating technology getting out of hand and how do you stop that? And yeah, so I would say quite exciting, quite interesting, possibly moving us in the direction of regenerative, needs to be researched, but it also needs to have the proper risk mitigation very robustly included in that process.
yeah, so there was some more comment about that in that question going on, whether we would
Mm,
have the same responsibility like we have towards a bicycle, etc.
yes.
Right,
And
yes.
I think, I mean, the thing is that a bicycle is not going to go out and self-replicate. This, no
Right.
bicycle I've
Yeah.
seen so far, right?
Yeah.
So when you build it, it's self-limiting. Something that can self-replicate, on the other hand, if it is able to harvest materials ambiently from the environment, what is the self-limiting, element in that, and what are the feedback loops that keep it from running out of, bounds?
Right.
Yeah.
Raj Gopal has a question, and we're trying to look at the definition once more. Why can't we define regenerative systems as systems with reversibility, with input and output to and from the system remaining unchanged despite changes in disturbance variables?
That's a very interesting one. I'm going to look into that one a little bit more. My first thought is that, you know, reversibility is a very interesting thermodynamic concept,
Yes.
right? Um, and what we're really reversibility, if something is going to be reversible, this has to do with the idea of the arrow of time, right? That entropy might help define the arrow of time. When you get into reversibility of a process, well, if a process is a entropy increasing process and it's reversible, then by definition, reversing that process basically reverses the increase in entropy inside of that subsystem, right?
Hmm.
As far
Hmm.
as we understand, the only way to do that would be to dump excess entropy make that a dissipative system and dissipate extra entropy into the surrounding environment, right? So I think we're going in the same general direction. I would be, I'm gonna have to like copy that down and like think about that a little bit more because it's a very
Well, I think
interesting way
I
of thinking
think
about it. Yeah,
I think we can give you a copy of all the questions with all the other details that I added,
be
and
perfect. Yeah.
then maybe we can pick up the discussion next time, or we'll put it into a collaborative group and continue the discussion. I think that would be very appropriate here.
Okay.
So one of the questions here is, would that mean that regenerative design is bio-inspired?
I would say that that is probably our first path. I mean, I don't think that we have seen anything in the science that tells us that bio-inspired design is the only way to get to regenerative. But the reason I kind of point out that regenerative is, I mean, life is at our moment the only actual active model of regeneration that we seem to have. And it's had a 4 billion year run at figuring out how to do it. So if I'm an engineer and I'm scratching my head and going, I got to figure out how to do a regenerate this difficult problem of regenerative design, right? Figuring out how to create negative entropy reliably in self-organizational structures. And I've got an actual example of it that has been debugged over a long period of time. I think I'd want to go look at that,
Yeah.
right? Instead of saying, well, I'm not gonna look at that, and I'm gonna go off and rediscover it from first principles, which is theoretically possible, right? It's theoretically possible that maybe we could come up with a way of doing it based around some other chemistry other than, carbon centric chemistry or so forth. I don't know. Maybe it's possible. But I would also note that this technology, the technologies that we as humans are using, are part of the living biosphere, and they either help it or they don't, right? And so my thought here is that if we want our technologies to be mutually symbiotic with the living world, to help it become more vital and more robust and to thrive so that we as organic organisms can also thrive, that it makes an awful lot of sense for our technologies to really work with seamlessly and create beneficial flows and interrelationships with the life that surrounds them. And therefore, I would say that not only is it our lowest hanging fruit to go towards more bio-inspired design, but it's more likely to move us towards technologies that are mutually symbiotic with the living biosphere if we start in that location.
Hmm. So there were a couple other comments here about like artificial neural networks were originally bio-inspired, but the
Yes.
later evolution into law of parsimony, like Occam's razor, and Kolmogorov's theorem of limiting them to three-layer networks do not make them regenerative. But Cohen self-organizing maps seem regenerative. So similarly, the later concepts of deep learning and convolution, no neural networks wherein complexity increases. Does that make them regenerative?
Yeah, what's interesting is that some of these things you could look at and say, ah, they themselves, when in their function, seem to be self-organizing. They seem to actually um, reverse entropy in that since they self-organize, they encode information in very complex ways, right? And in so doing, they themselves are highly negatively entropic. And so they're exporting entropy. And this gets into this interesting, by the way, I would love to be working with somebody who has really advanced understanding of the thermodynamics of mechanical statistics because, I'm an electrical engineer and I've had all the basic thermodynamics, but what we're pushing on here is how these ideas of, of mechanical statistics run up against living systems and so forth. So yeah, I'd love collaborators to have this conversation in more depth who have more of a advanced understanding of that mechanical statistics and the thermodynamics because these are great questions, right? But you're running these oftentimes you're running these kinds of neural networks on top of, say, silicon computational systems that themselves are degenerative and consume a lot of energy. Quite interesting, right? A lot of analysis to be done in that. And I think there's some fascinating questions. Um, Whereas life has figured out how to regenerate, um, you know, neurology over time and to self organize and self build. So it's like not only do the neurons, compute and create negative entropy informationally, but they also organize structurally, right? They self build and self organize structurally. So there's also mechanical negative entropy happening here. Quite interesting, right?
So, well, yes, it is. It really is. And it's been a privilege working with you over the last few years, exploring some of these ideas. We've got a number of other questions, but we have run over time. So I'd like to uh, maybe have put two more forward, but unfortunately, we won't be able to answer all of them. One of them is thank you for a very interesting presentation. In the final slide, you mentioned that a regenerative system produces more regenerative systems. Would it lead to a continuous positive feedback system?
And I think that's sort of the goal. And part of what I was trying to get at is that the every living system we've looked at, what typically happens is you wind up with some variation of von Liebig's law of the minimum, right? Which is there is some constraining factor to the amount of system complexity that can be articulated, and it has to do with the amount of available energy gradient, right, in
Mhm.
order to do work, or the amount of material that's available. In some cases, for example, we've seen certain ecosystems in which the biomass that can be generated is not limited by the amount of solar energy flowing through it, but is instead limited by the amount of, say, phosphorus that's available. It's like, well, we don't have any more phosphorus to build, right?
Mhm.
Or in some cases, it can be limited by information flows, right? And so we need to think about this not only in mechanical entropy, but also informational entropy. For example, we look at the fact that life encodes information in ways like DNA and so forth. It provides the instructions for the self-organization, right? And therefore, yeah, it's it gets interesting.
Yeah, so what's another one about what about swarm optimization techniques? Are they examples of regenerative design?
I think they can be.
Okay.
One of the things that I'll just do this one really quick. The Center for Bio-Inspired Design at Georgia Tech I've worked with Dr. Jeanette Yin. She's one of the co-founder of that. She's a professor of biology, and they did a whole thing where they were looking at emergent properties, and what they were able to they were looking at the problem of dispatching tasks to computers in a cloud compute situation. And theoretically, they were like, well, I mean, the common sense thing would be if you had a dispatch engine that understood perfectly the state of all of the compute engines, that by having that perfect knowledge of the state of all the compute engines, you should be able to, from that central command and control point, dispatch the tasks optimally, right? Because I know what the state is. And what, of course, happened with all the algorithms they had developed would they would hit maximum efficiencies that they could sustain. What they looked at was the fact that beehives, which is a swarm, right, actually have a work dispatch algorithm that is not centralized. Each of the individual workers has an algorithm for what kind of task that worker takes on. And so they took a cloud compute system and replicated this decision making so that that each of the compute nodes was a worker bee, and that it decided from its own standpoint what tasks to take on. So there was no central command and control. There was basically a pile of tasks to be done, and you had a completely distributed swarm decision making. And it turned out that that dispatch method was higher efficiency than they had ever been able to manage achieving with a centralized command and control dispatch, which is quite interesting. I think what you see over and over again is that this kind of distributed decision making is the solution that life has come up with in many cases to the kinds of decision making processes that humans have tended to drive towards centralized command and control. And so we're starting to understand that there are a lot of benefits to distributed command and control, including the fact that there aren't centralized single points of failure. They can tend to be more resilient. They can tend, if it's the right kind of task, they might be more efficient, and they can possibly scale in ways that centralized systems can't because of the ability to communicate state information across time and space.
Very interesting. And you use one of my favorite terms, single point of failure.
Yeah,
In any organization,
yeah.
a big problem. Okay, so unfortunately, we won't be able to answer all the questions. So we'll find a way of compiling maybe some answers and getting back to the attendees,
Yes.
either through a collaborative group or otherwise. And with that, I'd like to add my thank you to all the other thank yous that are already in the chat. Thank you very much for a terrific presentation. And we will look forward to discussing this further. I guess the presentation and the discussion I should thank you for. And we'll discuss it further at your next presentation. And hopefully in between or after the next presentation, we'll set up a little bit of a forum to discuss regenerative design and the various definitions and processes further. Thank you very much, Alan. It was a pleasure.
Thank you. Yes, thank you.
Thank you, Alan.